Carboxylic acids have several derivatives that we're going to look at. First of all, acid halides, acid anhydrides, amides, and esters. These are the four most common carboxylic acid derivatives. They undergo a common reaction. In the common reaction is that they all undergo nucleophilic addition, and notice what happens. The nucleophile attacks the carbonyl and makes a tetrahedral intermediate. Once a tetrahedral intermediate forms, you can have a leaving group leave. Do notice the tetrahedral intermediate. This is very important. Now, once the tetrahedral intermediate forms, you can have Y leave instead of the nucleophile. The rate of reactivity depends on how good a leaving group that the Y with a negative charge is. So if you have something that's a really good leaving group, this reacts quickly. If it's a lousy leaving group, it's not even going to react. It's going to, once it forms this, the nucleophile will just exit instead of cause a reaction to continue. Not only does a reactivity is determined by the leaving group ability, only if the leaving group Y is a better leaving group than the nucleophile, if it were to leave, will this reaction go forward. Otherwise, the reaction just goes in reverse if the nucleophile is a better leaving group. So let's go ahead and look at these. Rate the leaving group ability. Place these in order of leaving group ability. Well, if you look at this, the best leaving group is going to be chloride. So the chlorine with a negative on it. Then what's next? Well, that's going to be the acid anhydride with a negative on this oxygen here. Then the ester with a negative here. And then the amide's going to be the worst of all of the leaving groups because it would put a negative charge on the nitrogen. This is the order of derivative reactivity. So we see that acid chlorides are the most reactive and amides are the least reactive. The acid halides, you can have, this is an acid chloride right here. You can replace this chlorine with a bromine or with an iodine or with a fluorine. The most common acid halide that we have is acid chloride. Second most common is with the bromide. Acid chlorides are very reactive. If you put them in water, they explode. They react so quickly. To form an acid chloride, what you do is you take an acid right here, and we treat it with thionyl chloride. When we treat it with thionyl chloride, you get a derivative, this adduct right here, and then the chloride comes in and displaces it, and you end up making sulfur dioxide and hydrochloric acid. This actually breaks down to that. And that is how we form our acid chloride. You can form the acid bromide with phosphorus tribromide, and it does it with a similar mechanism. You're not going to be tested on these mechanisms, though. Nomenclature of the acid halides is you look and you say, what was the carboxylic acid that this came from? Then you remove the ic acid from that name and add il halide. So here's the example. That's propanoic acid. What do we do to change it to the acid chloride name? We take off the ic acid and put on il and then bromide. So this is propanoil bromide. So how do we name this acid chloride? Well, the first thing we do is we figure out what is this acid before you made it the chloride. That would have the OH right there. So let's name that acid 1, 2, 3, 4, 5, 6, 7. That's heptanoic acid. And on the number 5 carbon, you have bromo. So we would have 5-bromoheptanoic acid is the acid. Change it to the acid chloride by taking off the ic acid and adding il chloride. So it's 5-bromoheptanoyl chloride. What reagent do you need to make the compound above from 5-bromoheptanoic acid? Thionyl chloride. Acid anhydrides are basically two acids that have been joined together by the removal of water. You can make them that way, but it's kind of hard. You have to have special equipment and really work hard at removing the water. This is an example of an anhydride down here, maleic anhydride. It's highly reactive towards water and easily cleaves open to give the diacid. If we have an anhydride and it happens to get a little water in there, you end up getting the diacid very quickly. They're reactive. To name them, we name the acids, and then you remove the word acid from the name and add anhydride. If it's symmetrical, you're just going to be naming one of them. So you would just say, like if it was from benzoic acid, you would say benzoic, and then you remove the acid and add anhydride. So benzoic anhydride. If it's asymmetrical, you name each acid side and then add anhydride. Let's look at some examples. This is the anhydride made from benzoic acid. You can see that if you cleave this in half, you could put an OH here and an H there, and then you'd have two benzoic acids. So what do we call this? We take off the acid and add anhydride, and we call it benzoic anhydride. Here's an asymmetrical anhydride. This was propanoic acid. This is benzoic acid. So to name it, we say benzoic, propanoic, anhydride. We put them in alphabetical order. So go ahead and name these anhydrides. So for this first one, this is symmetrical, 1, 2, 3, 4, 5, 6. So it's going to be hexanoic anhydride. Here is asymmetrical. This is acetic acid, and this is 2-methyl-butanoic acid. So we're going to say acetic 2-methyl-butanoic anhydride. Esters are basically, if you take an acid and an alcohol and remove water, you make an ester. Once we form these, they are not very reactive. They're so non-reactive that we use an ester as a solvent. So ethyl acetate often is a solvent that we use, non-reactive. Neutral water will not cleave these. We can cleave anhydrides with neutral water. Acid chlorides are violently reactive with neutral water, but esters are stable to them. We can form esters by this equilibrium that we're shown here, and it's called the Fischer esterification when we do it. Acid and an alcohol, and what you do is you can form the ester if you remove water. Usually what we do is we add lots of alcohol or lots of whatever component we can find cheaply. If we want to take the ester, we can actually cleave it to the acid and the alcohol if we use acid, heat, and lots of water. To make the ester, we also have to use acid, heat, and lots of water. And we'll go into this equilibrium later. Esters are stable to water, so they have some water solubility. They won't react with them. They can hydrogen bond to water. Ethyl acetate has some water solubility, not a huge amount. It's enough that you can get a tiny amount to go in, but we consider it to be non-water soluble as a solvent because it's only a small amount that goes in. They cannot hydrogen bond to each other. They have a dipole-dipole attractive force because the compound is polar. But because they can't hydrogen bond, the esters tend to have relatively low boiling points. The boiling points and melting point are higher than that of the alkane because they do have a dipole, but it's much lower than equivalent weight alcohols or acids because those things can hydrogen bond. We say that above 5 carbons is water insoluble, but even 4 carbons, ethyl acetate, it's only a tiny amount that will dissolve in water. One thing about the esters is they are sweet smelling. So when you smell something like flowers, perfume, banana flavoring, those things are often esters. This shows how carboxylic and alcohols, which can hydrogen bond, have high boiling points compared to the same molar mass esters. You see how close they are to the alkanes? They're above them because they do have a small dipole, but it's really not a huge increase in boiling point. You really are closer to the alkanes in boiling point for the same molar mass as compared to the alcohols or carboxylic acids. To name an ester, what do? You look at the acid portion and you look at the alcohol portion. You name each of those. The alcohol comes first in the name, and we take the anol off and put "-il" on it. You put a space because this is now a separate carbon chain, and we then take the acid name, take the "-ic" off, and make it 8. Let's look at an example. This is an example right here. The acid side is right here. The alcohol side is right here. We call that phenol. And this would be 1, 2, 3, 4, 5 pentanoic acid, 3-ethyl pentanoic acid. So this is phenyl because we take an "-all" off and put "-il" on. We put a space and then 3-ethyl pentanoate. You take the "-ic" acid off and put on 8. Here is another ester. This is propanoic acid to chloropropanoic acid, and this is to bromoethanol. So now it becomes 2-bromoethyl space 2-chloropropanoate. So you go ahead and try to name these. Okay, this side is acetic acid. This side is phenol. So we write phenol and acetic acid. We take the "-all" and change it to "-il, and we take the acetic acid and change it to acetate. Here we have propanol. Here we have 1, 2, 3, 4, 5. That's pentenoic acid. So we've got propanol and 3-ethyl pentenoic acid. 3-pentenoic acid. We're going to change that now. We're going to call it propanil, or excuse me, not propanil, propyl. And then we're going to change this to 3-ethyl 3-pentenoate. Notice we keep a space between the two chains because they're separate carbon chains.